recording this one. So, rational numbers. A rational number are numbers, or rational numbers are numbers which can be written in the form of what? Using your extensive mathematical knowledge, a rational number can be written in the form of what? Not a function. So, let's think about rational numbers. Give me an example of a rational number. 1 is a rational number. You know it. 10. You know it. Only positive ones? Okay, negative 12. Only whole numbers? .5 is a rational number when written as 3 halves. Say what? In the form of a fraction. Okay? So any number written in the form of a fraction is a rational number. So like 12 over 1, or negative 12 over 1, or 1 over 1, or 10 over 1, or 3 halves. All of those are rational numbers because they can be written in the form of a fraction. Now, Christina, because I skipped over you when you said it right away, which was really good, okay, what do you think then is a rational function?
Oh, I don't know. I just got it. So,
Oh, okay.
Yeah.
Oh. Okay, so we'll open it up to everybody then. What do you think a rational function is? She's not. Function with a fraction is not right. Just stated a different way? Well, yeah, because you changed the words around.
Yeah, I don't look at it that way.
Anybody got a guess? A rational function is a function that has, I shouldn't even say it. It's a fraction with a function in the numerator and a different function in the denominator.
I thought you were going to word it how I did it. I was going to be joking.
Nope. Okay. So it's got a function upstairs and it's got a different function downstairs. Okay. So for instance, we could have something like f of x equals 7 over x minus 2. 7's a function. Call it a constant function. X minus 2 is a linear function. That's a rational function. We could have something like h of x equals 7x plus 2 over x squared plus 3x plus 2 on the bottom. That's a linear function on top, a quadratic function on the bottom, makes a linear, or makes a rational function. Okay? We could have, oops, let me move this down a little bit. Bless you. We could have that. That's a rational function. What's up, Freddie?
So, I'm not going to use g of x because that's really complicated. H of x, 7x and a 3x and a 2 and 2. Can we?
No.
I don't know if she's asking.
I know exactly what she's going to do.
Could you elaborate?
Yeah, she wanted to do this.
Yeah. Is it because they're different functions?
This is bad math. If I'm gonna cancel something out, right?
Yeah.
It's got to come out of both on the top. No, it doesn't. I didn't do anything to the 7x. You got to do parentheses. You got to factor. Yeah. 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 You probably heard me refer to this as the whack-off method. Okay? You can't just whack off the 2's. Okay? No. That stays. Okay? It's a function. Okay? So you got to factor it out.
That's what I do.
Yeah.
So,
Okay?
don't.
Now, there's one kicker to being a rational function. What is it? Think about what we have here now. What can't be 0? No. The denominator can't be 0, which is different than x being 0. In this first one, in f, x can be 0. Because I get negative 7/2. In this one, x can be 0. In h, I get 1. Okay? In this one, x can be 0. I get negative 6. Okay? You plug 0 anywhere that there's an x goes away, because if it's 0, gone, 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 12. Gone, 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 negative 2.
I was just looking at the bottom. I was like,
Yeah.
that's negative.
Yeah. Yeah. Go look at both, top and bottom. Okay? Alright? So that's the kicker. Because, unfortunately, what you should have gotten out of the last chapter, which some people got and some people didn't get, is that D word. Domain. The domain of a rational function includes all real numbers except the x values that make the denominator equal to 0. Okay? Okay? So the domain of a rational function includes all real numbers except x values, which make the denominator equal to 0. Now, last chapter, we were talking about two things that we had to look for. It's a bad F. What were they? Look for a radical. And a fraction. Good news. In this chapter, we're not going to have radicals. Bad news. All fractions. The entire chapter is fractions. Okay? Alright? So there's that. Now, next thing. that we have to talk about is the domain. You can write it as capital D for domain. How does the domain start? All real numbers. It doesn't end with all real numbers. It starts with all real numbers. A lot of people did it. And you guys were lucky that I was in a good mood. Okay? It starts with all real numbers. And then there's a condition. Okay? And then it doesn't start with x is greater than 4, comma, all real numbers, which was about 50% of the people on the test. Then there was about 35% of people that just put the condition down. And then there was only about 15% of people that got the domain questions right. Okay? That's how it looks. There is no changing that. Okay? From this day forward, if your domains don't look like that, are you right or are you wrong? You are wrong. Okay? That's how they look from this day forward. Alright? So, my question to you is, what happens in those spots where the denominator is equal to 0? So, let's try f of x equaling 7 over x minus 2. Our goal is by Wednesday to be able to graph these things. Okay? Which means we got to do some stuff today and some stuff tomorrow in order for Wednesday to work. Okay? We will graph 7 over x minus 2 or something very similar to it by Wednesday. Okay? So, what I'm looking at is where the denominator, x minus 2, I want to know where that is equal to 0. What do you got? X equals 2 is where that happens, right? So what then is my domain? All real numbers is how it starts. But x cannot equal 2. So the question then is, what happens on my graph at x equals 2? Because if it crossed the x-axis at x equals 2, my function would have a value at 2, right? So it's not possible. So something's got to happen at that 2.
Is there a hole?
No, it's not a hole. What kind of line? What kind of line? It's a specific vertical line. It's dashed, yep. Don't say vertical line test.
not saying vertical.
Even though Freddie wants you to say vertical line test,
She said
don't do it.
I was making fun of her because she said it's.
What is it? It's that thing. I'm guessing so far we've determined that it's vertical. Okay?
It's a hole.
He said it's no holes.
Oh, no.
It's not a reflecting thing.
It's vertical dash.
There's no holes.
Move on from the hole. We'll get to holes later on, but it'll take us like a week and a half to get there.
Okay.
But that is one of the 8 steps, is find the hole. This isn't the hole.
I remember this from last year, and I'm trying to.
I know. It's probably my second favorite mathematical word. It's spelled goofy. Say it loud. Asymptote.
The moment you said weird word.
What's my favorite mathematical word? Multiplicative. Rolled right off the tongue. Multiplicative. Okay? Okay? Vertical asymptotes. Okay? So, what is a vertical asymptote? It is, we've determined that it is a line, correct? That our function one, it does not cross. Because if it crossed the vertical asymptote, it would exist at that number. It can't exist at 2 in this particular case. Because at 2, we divide by 0. If x is equal to 2, I got 7 over 0, and that just doesn't work out. Okay? So it doesn't cross the vertical asymptote, and the function doesn't exist at that x value. Okay? We said that it is a dashed line. Okay? It's got to be on the graph. It's got to be on the graph. So up here, let's go back to this one. What would my vertical asymptote be? 2 is a number, not a line. X equals 2 is the vertical line associated with it. Okay? Notice where it came from. What about the domain? It's what it can't equal in the domain. Okay? Vertical asymptotes come from the domain's restrictions. Come on. however many numbers that make my denominator be 0. Okay. Now, I'm going to jump ahead here a little bit, and I'll come right back to this. Okay? So if I go all the way down to here, that's a nasty looking function, right? Okay? We're going to be able to graph that function in about 2 weeks. Okay? Right? Now, to make it easier on you, we're going to come up with a set of working guidelines. And if you follow those steps, there's going to be 8 of them total. If you follow those steps every single time, this is going to be like a cakewalk for you. Okay? If you decide to go rogue and go your own way, well, you might not have the most success in this unit. Okay? But if you follow these steps, it's boom shakalaka time. Okay? So, step number 1. For those of you that are using multiple colors and all that good stuff, you want to highlight this in some fashion. Okay? This is what you want. You need this. You got to know this because it's step 1, and you're going to use this on every single problem from now until Christmas. Okay? So you got to know this. Step number 1 is find the domain and any vertical asymptotes. How do you do that? How do we find the domain? But yeah? Bingo. So we set the denominator equal to 0. That's going to give us our restrictions. That's also going to give us our vertical asymptotes. That's where we start. Every single one. Even that nasty thing that comes at the end of the smart board. That's exactly the same place where we're going to start. Okay. Now, what I would like you to do is I would like you to find the domain the vertical asymptotes, and then use logic to describe asymptotal behavior and end behavior. We'll talk more about those behaviors. Okay? So, here we go. 1 over x is our function. I went basic for our first. Okay? What is the domain? Does everybody agree with all real numbers, but x cannot be 0? Okay? What is my vertical asymptote? X equals 0 is my vertical asymptote. What if I just put 0? It's wrong. So we've got all that stuff going on. Okay? Now, before we go on to end behavior and asymptotal behavior, I'm going to take a pause for the cause, and I want to talk about fractional logic. Okay? So, fractional logic tells me that if I've got a number and I divide that by a small number. Okay? If you have a calculator out, let's pick one. Let's do 1 divided by 0.1. Gives me 10. 1 divided by 0.01. 100. 1 divided by 0.0001. Should be 10,000, right? Okay? So the smaller that number gets, right, what is my result? Gets bigger, right? Let's try it with a different set of numbers. Instead of 1, let's do 10. 10 divided by 0.2, we'll say. 50, right? 10 divided by 0.002. 5,000, right? So that's still, no matter what the numerator is, if I divide it by an increasingly smaller number, that result is going to get huge, right? So this is going to become huge. Okay? So what I mean by that is some number divided by something going to 0, that's going to be infinity. The smaller your denominator gets, the bigger your result. Smaller your denominator gets, bigger your result. Let's change that around. If I take a number and I divide it by a huge number, it's going to get smaller, right? Okay, makes sense. Okay? Because now my denominator is getting bigger, so that means my numerator stays the same, so that's going to become a small number. Okay? So that's some number divided by something going to infinity is going to be, it's going to approach 0. Will it ever actually get there? No, but it's going to get closer and closer and closer and closer to that 0. Okay? Agree with me on fractional logic. Okay? So now, let's go back in here and let's talk about end behavior. End behavior is what my function is doing at x equals infinity and x equals negative infinity. The left and the right sides of my graph. We've talked about end behavior before. Okay? So in this particular case, as x is going to positive infinity, my function is doing what? So as x gets bigger and bigger and bigger, so I've got a number, positive number divided by a positive huge number. Where's that going to go? It's going to go towards 0, right? A number divided by a huge number, both positive, is going to go to 0, but we're going to add something in here. It's going to go to 0 from above. Because it's positive. It's getting closer and closer to 0 from the positive side. As x goes to negative infinity, f of x is going to what? So now my number is going, it's getting a big, but it's negative, right? So I've got positive 1 divided by negative ginormity. No. It's going to go to 0 from below, because it's going to be negative now. So it's going to go to 0 from below. So that's my end behavior. Now, we got this new one called asymptote behavior. Okay, so now it's as x. Oops. Just start over. As x approaches 0 now from the right, what does my function do? So basically, on the graph, you're going to have this vertical line. Okay? And your function's going to be approaching it from the right. But it can't just stop. It's got to go somewhere. Okay? So it's either going to have to go up, or it's either going to make a turn and go up, or it's going to make a turn and go down. But it can't just stop because it can't cross over it. Okay? So that it's going to turn and go up, or it's going to turn and go down. So, my function again was 1 over x. So as x approaches from the right, that means I'm getting smaller and smaller and smaller, but I'm positive. Right? So a number divided by a small number, that's positive, is going to go to which kind of infinity? Positive infinity. Then, as x approaches 0 from the left, what's our function going to do? Negative, because now I'm going to be negative, a really small negative number, and it's going to go down to negative infinity. unfortunately, there is no shortcut to that. You've got to do the logic. You've got to stop and think about it. Okay? If there were an easier way, I would teach you, but there's not. Actually, I lied. The easier way is graph this function and look at the graph, and you can tell it right off the graph. We're going to get there. Wednesday, we'll do that. We'll pull it right off the graph. And we'll just say, oh, it's this, it's this, and it's this. Okay? Because it'll all be there for you. Okay? Try that one. Domain. All real numbers. Agree with x cannot equal 4. Okay? Which means that my vertical asymptote is x equals 4. Okay? Forgot to put that on. Okay? So my end behavior then, as x goes to infinity, f of x is going to positive 1 divided by a positive big number that's going to go to 0 from above. As x goes to negative infinity, f of x is going to go to 0 from below. Asymptotal behavior. As x goes to 4 from the right, my function is going to go to, well, here now, that's going to be 1 divided by, if I'm on the right side of 4, like 4.1, right? 4.1 minus 4 is going to be 0.1, positive. So that's going to be a positive small number. So that's going to go to positive infinity. As x approaches 4 from the left, f of x is going to go, now it's going to be 1 divided by a negative small number. So that's going to go to negative infinity. Okay? I got 2 good news and I got 2 bad news. One good news, you don't need to bring your books anymore this calendar year. Okay? Because there's no homework out of the textbook in this section. Okay? I don't need it. Some people do. Okay? Bad news to go along with that. There's homework, but it's a pack. Okay? Alright? Another good news. There's no homework tonight.
Thanks, Lynn.
Okay? Bad news. It's a big long packet.